here I have two Euler vector fields, d by dzk plus 1/2 sum of zk bar dzk bar. See, there are these two contributions. Now, there was a formula for them. Now if we consider what is the Teichmüller floor, I start deforming my Riemann surface. And now I ask the following question: how the matrix of B periods changes when I make this deformation? Of course, the conformal structure changes and the matrix of B periods changes, but it changes somehow, in a sense, quasi-periodically. So this complex geodesics, it starts and then it comes, you come close to your Riemann surface many times, and then you average your matrix of B periods along this t direction. And essentially it turns out that, of course, asymptotically it has some limits. So asymptotically you will get initial matrix of B periods times some other matrix. And you look at the eigenvalues of this other matrix. And these are called these Lyapunov exponents, roughly speaking. And what is of interest for the people in ergodic theory is this sum of the Lyapunov exponents, lambda 1 plus, etc., lambda g. And for that, there is a formula up to some constant, formula again derived by Kantsevich, I think. So here you have integral over the moduli space. In the case of arbitrary stratum, AG, M1, etc., MR, of dd bar log MB. So you have the times, of course, you need to multiply with some other form to which what was this form? It's some volume element, the volume element in the complement. But because here you need the full dimension, here you just get the two coordinates, and you need the complement. Now, what these guys did, you see, to compute this integral, since AG is highly non-compact object and it has a lot of singularities at the boundary, they were unable to understand how this thing behaves when you approach the boundary. Somehow the asymptotic seems to be quite unpleasant. In particular, there is a dependence on the Tarelli marking here, and on the choice of canonical basis. You have lots of logarithms. So what they did is they rewrote this formula, this object, in terms of determinant of Laplacian. And for determinant of Laplacian, the asymptotics can be computed much better. So they have derived the formula which we get right away from our formula also. It looks like that. You see, if you now multiply, well, put this to the right-hand side and put dd bar to both sides, then in the right-hand side you get dd bar of that in B plus dd bar of logarithm of this area, because I forgot that. And of course, when I start differentiating the area with respect to t, I get 0, because area is, once I factor SO2, then the Teichmüller deformation is area preserving, right? And what is left? So let's do that roughly. So what I get is dd bar log delta is equal to dd bar log that in B the area doesn't give us anything, and plus dd bar log tau plus log tau bar. And you see, one would expect, if the Teichmüller coordinate would be holomorphic, if the Teichmüller disk would have been embedded holomorphically, then here would have got 0. But if I look at this formula, this term, of course, gives me 0. But these two, when I apply the vector field, I get just the earlier vector field to log tau. I just get the homogeneity factor, which stands here. Well, in the case of arbitrary stratum, so it will be something depending on the multiplicities of the zeros. Roughly speaking, the formula will be like that. So what you get here is a number, actually. It's an explicit number, and we were quite surprised that we found exactly the same number in Eskin-Kantsevich-Zorich formula. So plus 112 sum over k, mk, was it m? mk plus 2 divided by mk plus 1. So this is what so initially in the sum of Lyapunov exponents, you have the curvature given by that in B, but after, well, if you want to really compute things, then you have to go to log that delta, which behaves better on the boundary, and then they work with log that delta and get, in some cases, get explicit answer for the sum. So essentially I have finished with that. I don't know, should I say something else? Maybe I can say a few words about this Riemann-Hilbert problem which underlies the tau function in the Hurwitz case. I have another about 15 minutes or something, so I can speak how one builds a solution of the Riemann-Hilbert problem corresponding to the tau function. And this Riemann-Hilbert problem is interesting by itself. People use this kind of problem as asymptotical Riemann-Hilbert problems in the theory of random matrices. The theories of Deift, Zhu, and their co-workers, when they ask the questions like how to find the asymptotics of a partition function of certain matrix model. Then from the matrix model, you get some Riemann-Hilbert problem which is typically unsolvable. You get the monodromy matrices about which you know that such Riemann-Hilbert problem cannot be solved. But then you usually have some small parameter or large parameter, depending how you look at it. And then in the limit, you know that your Riemann-Hilbert problem can be approximated by something solvable. And this something solvable is usually one of these quasi-permutation monodromy matrix Riemann-Hilbert problems. And the solution, so solution of a Riemann-Hilbert problem with quasi-permutation monodromies. So let me recall that we are in the situation of Hurwitz spaces. So let's take the Hurwitz space for simplicity H, G, N, 1, 1. All poles have multiplicity 1. And I have a bunch of branch points. I have my function f. And I have some base here, the z-plane. And the formula for the psi function for the solution of Riemann-Hilbert looks as follows. I need to choose some normalization point, z0. And suppose I want to compute my psi function, well, at some point z, somewhere here. It's sufficient to take a small neighborhood, then I will analytically continue. Now, let's introduce the following notation. Fix some splitting of my Riemann surface into sheets. So each point has exactly d pre-images here, except the branch point. Z0, we assume that it doesn't coincide with any branch point. So let's enumerate them. Z01, Z02, Z03, etc. Z0d. Take point z, also lifted on different sheets. Get Z1, Z2, Z3, etc. Zd. Now my psi function will depend on point z and on point z0. So psi at z equals z0 is going to be equal to 1. This is the normalization point. And the formula is going to be like that. I take some Siga kernel on my Riemann surface between points z and z0 and divide with Siga kernel S0, which is the Siga kernel on the base between z and z0. So what is S0 here? S0 is simple. S0 is just square root of dz square root of dz0. These are two spinors divided by z minus z0. And S, the Siga kernel on the covering. Oh, I'm sorry. So I have to say, of course, I need jk component, and here I am going to put zj, z0k. So I take the Siga kernel between point number j sitting on top of z and point number k sitting on top of z0. So I have all these pairwise combinations, and I take Siga kernel between any two of them. And in the denominator, I always have the same. So you see, of course, well, this is in principle tensor. This is tensor, but the ratio, if I write it in the local coordinate lifted from the base, then I can write local coordinate on the covering in terms of local coordinate on the base, and differentials I cancel out, just some scalar factor remains from the change of coordinates. So what is the Siga kernel on the covering? It's the following thing. Between points x and y, I take some theta function with characteristics p and q and compute it at the Abel map between points x and y. And in the denominator, I have theta pq of 0 times the prime form between x and y. So locally, the Siga kernel on the diagonal, it behaves like that. It has simple pole. It's, well, you see, E, the prime form is -1/2 differential. So Siga kernel is 1/2. It's spinor with respect to x, spinor with respect to y. And of course, there is also additional, if say y goes around some basic cycle, of course I get some factor of automorphy, which will essentially. Well, it's a constant factor. Essentially, this with respect to x, it's a section of the line bundle chi pq, which is a flat line bundle with automorphic factors along a cycles given by compo e to the power 2 pi I pi, and with respect to b cycles, automorphic factors are given by the components of the vector q. So then I get a flat line bundle chi pq, and I tensor it with the spin line bundle. So this is with respect to x, and with respect to in x, and in y it's a section of chi pq to the -1 h delta. So that's some kind of Cauchy kernel. It's a reproducing kernel in this line bundle. So if I take the ratio of these two guys, then essentially all the singularities of this object come from the difference in local parameter in the neighborhood of branch points between the base and the covering. And you see what happens if I now try, well, if I start from some neighborhood of points at 0, and if my z travels around some loop encircling one of the singularities, then, well, the points, these points on the covering, they go around and they interchange somehow when I come back. And once they interchange, the columns of this guy interchange. But also, I may get some additional factors because, well, I can cross the boundary of the fundamental polygon. And then these additional factors will depend on the components of these two constant vectors which I put here. So essentially, since I have these additional constants in the Sige kernel, my monodromy matrices will not be just the permutation matrices, but they will get some multipliers. And in this way, I'm going to construct a solution of Riemann-Hilbert problem, and then the tau function corresponding to this will not, strictly speaking, coincide with the one which I was defining. The tau function of this problem will look as follows. It's tau function which I defined to the power -1/2 times the theta function with characteristics p and q computed at 0. And this factor is important. You see, this thing, essentially, it never vanishes. But this factor, it vanishes once the vector bp plus q hits the theta divisor. And at these points, my Riemann-Hilbert problem becomes unsolvable. So I have a jump, well, or I have to adjust the solution, or I have a pole in the solution of Schlesinger system, depending on the point of view, but it's an essential part. The tau function itself, which I have defined, it's a tau function of another Riemann-Hilbert problem, which appears in the theory of Frobenius manifolds. And where the monodromy matrices are different, the solution is different, and it's other part of the story. So essentially, the same object appears in two rather different Riemann-Hilbert problems associated to Hurwitz spaces. It's just one of them, and another one comes from the theory of, so another Riemann-Hilbert problem from Frobenius manifolds. Their tau function is just equal to tau Jimbo Miwa is our tau. Here, Jimbo Miwa tau function is tau to the power -1/2 times theta pq at 0. Now, one last comment is if you say open the classical works from year 85, 86, 87 of string theorists, then you find that this tau function was, well, they wrote relations of the following kind. Determinant of the bar operator acting in spin line bundle with twists is equal to determinant of D0 d bar operator acting on trivial line bundle times theta pq at 0. And they didn't define these objects rigorously. For them, these were various partition functions. That was pure formal relation. This relation is not formal. Here we know what are these objects. So we got explicit interpretation of their formal exercises at that time. Here we have explicitly defined tau function of different Riemann-Hilbert problems. Well, we know the interpretation of these objects in the formulas of holomorphic factorization, so we basically can decode that. So I think now I exhausted all my knowledge in this area. I have to stop. Thank you.
Some Riemann surface, for example, hyperelliptic, has a differential, if I understand correctly, whose zeros consist of only one constant, right?
Zeros.
Zeros of argument.
I would right away I can tell how to get a differential with zeros at 2 points, right? At infinities. If you take something, well, just take d lambda over the square root of your polynomial, then you get all zeros. Yeah, if you if you have y square equals polynomial of x, then say if you have dx over y, so this guy has, but it has 2 zeros. About 1 0. No, I think even in genus 2 there are 2 strata. There is one stratum H11 and another stratum H2, which has codimension 1. So which means that not on each Riemann surface. In genus 2, each Riemann surface is hyperelliptic. But yeah, but of course on each Riemann surface you can find the differential of degree 2. That's right. The differential with 0.
Okay, what your formula can be for the half function? How does half
for the hyperelliptic case, genus 2, 1, 0. I don't know. I have to compute.
I wonder
Yeah, that we should discuss. If I think a little bit, I may say that, but.
Any other questions? I have one question. Comparing Jingbo's mu formal equality, you showed that you proved another equality between tau tilde. It looks like that tau tilde is corresponding to the determinant of the Dirac.
Yeah. That's. Oh, I'm sorry. I forgot to put -1/2 here.
So then the.
Yeah, exactly this.
So that means that you derive similar equality for the tau tilde and the determinant of the Dirac calculation.
No. That we don't know.
Right? So you
Well, so somehow this part we know explicitly, but this part we didn't really know. No, the spectral meaning of this correspondence we didn't study. That's a good question.
But I'm asking, using your message, you have somehow feel.
Well, one has to know what to prove at the moment. One has to define for this flat matrix. One has to look at.
What actually you can define invariants of the
Yeah, but you see here you have some the space is not. You have these twisted spinners.
Yeah, but I think that's right to define.
Yeah. I suppose it's a good question. Somehow we didn't pose it, honestly. So
Okay, any other questions? Okay, then let's next speaker again.